All right, so 10.3 vector valued functions. So we talked about vectors yesterday. You've got a couple ways of writing just a regular vector. Let's say u is 5, 12. That's called component form. Another way to represent u as a vector would be 5i plus 12j, and that's called a linear combination. I feel like this is the version that we're going to spend more time on in this section, so the linear combination. So I represents the horizontal, j represents the vertical. If I wanted to set up parametric equation representing this, so what would this vector look like? It's got 5, 12, so we go over 5 up 12. That has a magnitude of 13. So both of these would be that vector right there. If you wanted to represent that with a parametric equation, and let's say this is at time equal to 0, and this would be at time equal to 1, that would be the easiest scenario to do time 0 as initial and time 1 as the terminal. Then it would be x equals 5t and y equals 12t, and it would be from 0 to 1. So where is the particle, if it was a particle, at time equal to 0? You could plug 0 in for x, 0 in for y, and you get 0, 0. So that is our initial point. If I plugged 1 into each of them, I would get 5, 12. That is my terminal point. So this is a parametric representation of the vector. Okay, now I'm actually just going to open the book and page 533. You don't have to if you don't want to. I'll just put it up here. Okay, so R is a position vector of a particle moving along a smooth curve in the plane at any given time t. So the velocity is the derivative, that's not a shock. The absolute value of the velocity, which is the magnitude of the velocity, and that's the speed. So that's also consistent with what we have been doing. But if our vector was this one right here, and that represented our velocity, how fast is this particle traveling? Sorry, I'm moving it all over the place. How fast is that particle traveling? It's 13 units per whatever, right? 13 meters per second or whatever it is. Yep. But the vector itself has two different components, the horizontal and vertical, but the magnitude, which is the absolute value of the vector. Now, absolute value, we've always thought like on a number line, it represents a distance. Have you been told that, or have you thought about that? Yeah. Like on the unit, like on a number line, if I had 4 and -4, what's the absolute value of -4? You could ask yourself, what is the distance of -4 to 0? Its distance is 4, so it's always positive no matter what. So for this one, if I want to know the absolute value, then we're just finding the distance traveled. Again, it's in 2 dimensions, but it is the distance traveled, and that would be the absolute value, which would be its magnitude, which is 13. All right. Number 3. So acceleration is another derivative. It's the derivative of velocity. And then a unit vector, we talked about this yesterday. Remember, if we wanted to find the unit vector, all you need to do, the shortcut, is to divide each component by the magnitude. Like you could set up similar triangles and figure out a unit vector, but the easiest would be to just divide the velocity vector by the magnitude of the velocity, and you have a unit vector. So keep in mind, v right here, that is like a component. That's a I and a j components. So if you divide each of them by its magnitude, then you have still a vector, but it's a unit vector. All right, this is very important. Important enough for me to put a star next to it. So velocity equals, I'm going to write this down. We're writing again. So velocity equals absolute value of v times v over absolute value of v. Okay, so this right here is speed. Right, we just talked about the absolute value of velocity is its speed, and the velocity divided by the absolute value, that's the unit vector, which is considered the direction. So unit vector is the same as its direction. If you want to know what direction it's going, you'll make a little mini vector, which is a unit vector in the correct direction. All right. Hold up. Pause or continue?
That just makes the velocity equal the velocity.
Yeah. Yeah.
I
So
think we don't know this. This is not like intuitive.
that's a really good point. So if you look at that, these cross off, right?
Yes. Yeah.
So you get velocity equals velocity. Well, I would hope that velocity is equal to velocity. But sometimes you're going to be given, and I don't know. You're going to be given different parts of this equation, and you could just kind of land on the fact that this is a true statement. They'll tell you to find a unit vector, and then write the velocity equals this times this as an equation. It's just something that they will do.
There's only like 2 parts. There's only one.
So it looks simple enough, but keep it in mind, and you literally have to look at it and just kind of let it sink in sometimes. At least that's what I found to be true. So we'll come back to it if you want. I know, yes, it's important and worth noting that these will just cross off and you get velocity equals velocity.
Yeah.
But it does serve some purpose. All right, example 5, getting into some applications here. Let's study some motion. Okay, so the vector, this, is a position vector. R is considered like a position with vectors. So of a moving particle at time t. So if you wanted to know where is the particle at time 0, you could plug in 0 spot on the graph. You'll go this horizontally, that vertically, and you'll have a dot. That'll tell you where the position is. So the velocity, we're supposed to find the velocity and acceleration vectors. So it's what you would think, I would even use the word intuition, that the velocity is just the derivative of that, and then the derivative of that, and you've got your velocity function, or your velocity vector. So the derivative of the horizontal would be, what, negative 3 sine t. This would be 3 cosine t, and you can see that that is our velocity, negative 3 sine t I plus 3 cosine t j. And if we wanted the acceleration vector, just do another derivative, and it will give you the acceleration at any given time. Okay, so the velocity, acceleration, speed, and direction of the motion at t equal to 4. So we simply type or plug in pi over 4 into this one, these vectors that we already have. the speed at pi over 4. So here's them plugging in pi over 4 into their velocity and acceleration. And this is the velocity and acceleration at t equals pi over 4. The speed is the absolute value of the velocity at pi over 4. So that's like our finding our hypotenuse using the Pythagorean theorem. We know what the velocity vector looks like. It's right here. So let's find out its hypotenuse, and that's how fast it's traveling. That's our speed. And then the direction is our velocity vector divided by whatever the speed is. So we're dividing it by 3. So divide each of the velocity components by 3, and we get our direction vector. That is a unit vector with magnitude 1 in that direction. Okay, let's see. So let's say I wanted to know, I've got a graph on the next page. So this is the, right here, catch up camera. So if I wanted to know what is the position at time equals 0, let's do that. So let's go back here. Actually, we could just use the one that they have. Did they ever figure it out its position at pi over 4? What's our position at pi over 4? So it's right here, right? So if we plug in pi over 4, it's not easy to do. So it's what? Square root of 2 over 2 times 3, 3 square root of 2 over 2. Okay, so our position at pi over 4, you would get that ordered pair right there, whatever that dot is at pi over 4. Our velocity at pi over 4 is a vector at that point. You can see that the velocity at that time is this right here, that red vector. So if you plug pi over 4 into our velocity vector, it's going to get this vector right there. So imagine, like, you know what centrifugal force is? What is that?
Water bucket and spinning it.
Exactly. So if we're like spinning this around with a water bucket, at any given time, let's stop right there. What's going to happen to the water bucket if we let go? It's going to take off in that direction with that speed at that given time. Okay, so we can find its position right there, but what's its velocity? It's going to be going off just like that. And what's the acceleration? It's actually perpendicular, orthogonal, or normal to this right here. It's actually going in right here. So on the water bucket, what force acceleration is acting? I don't know. That might be too tough a question for me. I think it would be the centrifugal, right? So there's force going off. The water wants to take off in that direction, but there's got to be a force acting against it because it's not going anywhere, right? So the bottom of the bucket is acting that way, and maybe that's the acceleration pushing back. I don't know, I might be making that up. Okay, but you do know that the acceleration is going back based on the math at least. So the last part of this question says v dot a equals 0. So if we do a dot product with a velocity and acceleration, we talked about this a little bit yesterday, what happens when we get 0 for that? What does that mean?
It's orthogonal.
It's orthogonal, very good. So it's either one of the two is a 0 vector, 0, 0, which is kind of lame, or they are orthogonal, which they are. And they're orthogonal for all t. So no matter what, like right there, our velocity is going to be going here, and our acceleration is going to go here. They're always going to be orthogonal with each other. All right, example 6. We're still studying motion here. So vector that gives the position of a moving particle. Write an equation for line tangent. to the path of the particle at the point where t equals -1. Okay, so equation line tangent. So if it was just a regular calculus problem and you wanted to find the line tangent to the curve at a point, well, it's t equals -1, so it has to be parametrically defined. But you need to know its slope and you need to know its one point, right? Ordered pair. So we can find its slope. I think it's the derivative. So our derivative, or velocity, is right here. You can plug in -1, and our velocity is going to be 12I minus 9J. Okay, so that's our rate of change, but you just have to make it the rise over the run, so the vertical over the horizontal. So if our rate of change at -1 is this, it would just be -9 over 12, which is -3/4. So our m is -3/4. Just do the vertical over the horizontal to get its slope. We also need to know an ordered pair. We've got our position equation or vector right up here, so you can just plug -1 in. Looks like the book did that, -1, so you get -5I plus 11J, which is basically -5, 11. So then it's just an algebra problem. You got your ordered pair, you've got your slope, and you get your equation. B, find the coordinates of each point on the path where the horizontal component of the velocity is 0. So the horizontal component of velocity is it's when your vertical rate of change is 0. So that's your, so when the horizontal component, it's not vertical, it's the horizontal is right here. That's your horizontal, so you could just set that equal to 0, and you get, what, 0 and 6? Oh, 0 and 1, sorry, I'm trying to do algebra in my head. So if you pull out a 6t, you get t minus 1, so you get 0 and 1. So it happens in two places where you have a horizontal component of velocity, which is 0, and then you can plug 0 and 1 in, and you get your points, your ordered pairs, into the position position vector. Questions so far? Making sense?
What questions to ask.
Are you like overwhelmed? Or is it like it's making sense as I do it, but it's just a lot of information?
What's with the b of the -1? Why would that not just be, like, why wouldn't that just be -3? Like what?
So if we want to know like the slope, we're trying to find the slope at that point. You've got a horizontal 12 and a vertical -9. So the slope is rise over run, so -9 over 12, you get -3/4. You do that when you're trying to find the equational line tangent to the curve and you want to know its slope at that point. That's what you got to remember. Just do that over that. Other questions? Looks like I have, well, I was going to go through 7, 8, and 9. Well, we're doing all right.
We have online people?
Would you say online people?
Yeah.
Yeah, they're both here, yeah.
Okay. I don't remember talking about this.
Example 7, finding antiderivatives. Okay, so integral of a vector, you just find the antiderivative of I, antiderivative of j, and you get your answers. And you could do a plus c at the end. That'd be for an indefinite integral. Number 8, I wrote, let's see. Okay, so we've got a definite integral here, number 8. So to find a definite integral, again, you just, as you would think, you find the antiderivative of that, I, antiderivative of j, and just evaluate it. In this case, you end up getting negative pi squared j for an answer. So what did we just find? If this right here was a velocity vector, you found the, well, it almost position, but it would be displacement.
Yeah, that's what
Yep, because we have an interval from 0 to pi. So what does that mean? That the particle, or whatever it is that's moving using this as its velocity vector, from 0 to pi units of time, it has gone down pi squared units. And it did not move horizontally in that time interval, because its horizontal is 0. Okay, so definite integral, kind of like what we would do before, just the antiderivative, and it gives you the change in whatever. In this case, it would be displacement. All right, number 9. Kind of a cool question. See if I can find it here. Got all my pencil note marks in my book here. Not that I can read them anymore. The velocity vector of a particle moving in a plane is that. So that's our velocity. Find the particle's position as a vector function if r of r equals natural log 2I when t is 1. So this is an initial value problem. They give you the velocity. You need to not find its position, given that when time is 1, r, or the position, is natural log 2I. Okay, so we find the antiderivative right here. And you get natural log t plus 1. They use parentheses here because our time is always greater than or equal to 0. So it would be redundant, and they would never want to be redundant. So they use parentheses. So you do get a c here. We need to solve for c by using an initial value. So we know that r is natural log 2I right here. And then what's our equation? Oh, right here. If I plug it in, I get natural log 2I plus j, because t is 1. You get this. So that's our equation. You need to solve for c. So I subtract a natural log 2I from each side. That disappears. If I subtract j, c is negative j. There's our c is negative j. So c is negative 1j. So if you wanted to, we had natural log of t plus 1I. We had t squared j. Now we have to incorporate a negative 1j, so that becomes a t squared minus 1j. And that's our position equation. You'll have some practice. That's a little confusing. It's pretty confusing. You'll have some practice with that stuff. I can make them up too, but yeah, that's kind of how you do it. B says find the distance particle travels. So the book shows that you turn it into parameterization, or like parametric, and then just use our integral, the square root of dx dt plus r squared plus dy dt squared, and you get some number. I think that's it. That's 21 minutes worth. Questions worth recording?